In this lesson, we are going to discuss the third use of a potentiometer. It is to find the internal resistance R of a cell. So here we have to do two experiments. So this is our potentiometer, EMF E, internal resistance R connected to a potentiometer wire. So this is our potentiometer wire. And we take the same equipment and keep it ready again. So we'll be doing two experiments. So that's why you've drawn two diagrams. In the first experiment, we take the given cell whose EMF is E1, internal resistance is R1, and then we find the balance point, the point at which the current through the galvanometer is 0. So the balance length is, say, L1. Now we have seen earlier that E1 will be given by Z into L1. Here the internal resistance does not come into picture because no current is flowing through this when we are at the balance point. So we can find the EMF exactly, and that will be Z into L1. Z is the potential drop per unit length. The potential drop here is equal to the EMF of this cell. Now we take the same cell and connect it like this. Now we want a current to flow through this cell so that this R1 comes into picture. So we connect a known resistance capital R to this circuit. This is known to us. And then we find the new balance point. So once we do this, some current I1 is flowing through this cell. So there is a potential drop across the internal resistance. Now this balance point will correspond to the terminal voltage, and that terminal voltage is given by E minus I1 R1. We can also apply Kirchhoff's law and understand that E minus I1 R1 is the potential difference between these 2 points, and that is equal to the potential drop here. Like here, the potential difference between these 2 points was E1, and this was equivalent to the potential drop between this point and this point. Now here, the potential drop here is equivalent to the potential drop across length L2, because this is the new balance length. So therefore, if you apply the principle of potentiometer, E1 is equal to Z into L1, and E1 minus I1 R1 is equal to Z into L2. We want to find R1. Okay, so we can subtract the two equations, so E1 will get killed because we don't need E1. So we'll subtract 1 minus 2. So equation 1 minus equation 2 will give us I1 R1 is equal to Z L1 minus L2. L1 is more than L2 because here we are measuring E1, and here we are measuring E1 minus I1 R1, the terminal voltage across the battery. Now I1 we can find out because I1 will be this EMF by the total resistance in this circuit. This circuit is now independent of this because there is no current flowing through the galvanometer. So therefore I1 will be equal to E1 by R1, small r1 plus capital R into R1 equal to Z L1 minus L2. Now what is E1? E1 is nothing but Z into L1. So we can write this E1 as ZL1. So Z will cancel. And now we can solve for R1. So we get here L1 R1 equal to L1 R1 this into this plus L1 capital R minus L2 R1 and minus L2 capital R. So L1 R1 cancels. So L2 R1 is left. So this we take it this side. So we get R1 equal to L1 minus L2 divided by L2 into capital R. So this is how we can find the internal resistance of a cell using a potentiometer. Potentiometer gives us the exact value of voltage. So that is the advantage of this equipment because it does not disturb the original circuit. So here first E1 was connected, we found the balance length, the E1 became Z into L1. Then once we connect an external resistance here, current flows through this circuit. And then the potential difference across the cell is equal to the terminal voltage. Terminal voltage is given by E1 minus I1 R1. So now we have got two equations, one for the terminal voltage and one for the EMF. E1 is Z into L1, the terminal voltage E1 minus I1 R1 is Z into L2. Since we don't know E1, we subtract the two equations, E1 goes out of the equation. Then I1 is equal to E1 by R plus R. So we put that, again we got E1, but E1 is Z into L1. So Z is cancelling out. And once Z cancels out, R1 becomes L1 minus L2 because L1 will be more than L2. L1 minus L2 divided by L2 into capital R. Capital R, the external resistance that we connect here, that is known to us.